So let's move to the last presentation of this block by Kyohei Akiyama from JAXA, and it's about QZSS satellites integrated with LEO onboard GNSS observations.
Okay, good morning, everyone.
Oh, sorry, I missed the part of the title. Precise orbit determination of QZSS satellites.
Thank you. Thank you for clarifying. I'm Kyohei Akiyama from JAXA. So today I'd like to introduce a precise orbit determination QGIS satellite using conventional, not only using the conventional ground station data, but also using the LEO onboard GNSS observation. This is agenda of this presentation. And currently, as you know, several types of GNSS orbit are using, and the GNSS satellite, GPS, Galileo, GLONASS, and the most part of the Beidou 3 satellite are placed in the middle Earth orbit. And the RNSS, like QGSS, and the rest of the Beidou satellite is placed on the geostationary orbit and inclined geosynchronous orbit. And as seen from the ground, the GNSS satellite motion such as GO and IGSO is stable or very slow motion, so which makes it difficult to determine its orbit position precisely. So this is motivation of my study. And regarding the precise orbit determination for IGSO and GEO satellites, the main problem is a poor observation geometry with respect to the ground tracking station compared with the MEO GNSS satellites, which lead the strong correlation between the orbital element clock offset and ranging bias, such as receiver intersystem bias and phase ambiguity. In particular, along track orbit position in GEO satellite and phase ambiguity has a strong correlation. So the using carrier phase measurement has no longer contribute to determine the position, along track position in GEO satellite. So the one of the realistic option to cope with such kind of problem is applying the on-orbit monitoring station. The concept of the on-orbit monitoring station is a multi-GNSS receiver mounted on the LEO satellite constellation. So after downlink such kind of observation, the ground segment can perform the ODTS using not only the ground-based observation, but also using the space-based observation. So the main component of the concept of the on-orbit monitoring station is a LEO constellation, multi-GNSS receiver, and POD software integrating space-based observation. Sorry. Wow. Sorry. I want to move back to the presentation. Sorry. Okay. Thanks. Okay. So fortunately, we had an opportunity to demonstrate the concept of on-orbit monitoring station using the on-orbit observation data as a part of the JAXA's onboard PPP experiment, where the real-time navigation using the Madoka PPP correction message from QGIS satellite. So the concept of the on-orbit PPP experiment intended to perform the real-time navigation, but these data are also used for the demonstration of orbit monitoring station as post-processing basis. So the GNSS receiver and antenna for the experiment are mounted on the QPS 10 satellite, which is developed by the Japanese private company, and we provide the navigation payload as a hosted payload. So This slide shows the data of our navigation payload. The GNSS receiver and antenna can track the multi-GNSS and multi-frequencies such as GPS, QGIS, Galileo, Beidou 3, and GLONASS. And navigation payload have the two redundant lines to receive the observation data, which is very helpful to validate the orbit quality of the rail satellite to compare with two different type of observation. And the navigation payload also have the laser reflector array for LEO POD validation. This reflector has developed by JAXA. And this slide shows the data quality assessment we conducted. To assess the data quality, code minus carrier observation with ionosphere-free ionospheric correction are applied for that assessment. And according to these two plots, the left plot shows the code minus carrier combination using the onboard data, and the right shows the using the IGS station of NOR station. So according to these two figures, we can see the relatively higher error in GPS L2 band compared with the station on ground, but we also see the less multipass error, multipass and noise error at low elevation in L1 and L5 band. And I also showed the POD validation for rail satellite. And this plot shows the orbit difference between the orbit solution using the independent GNSS observation, like antenna 1, receiver 1, VS, antenna 2, and receiver 2. And we can see the excellent agreement between two solutions. And we also see the SLR residuals using two types of orbit solution. And this indicates the rail orbit are estimated with an accuracy of a few centimeters. So it can be applied to the demonstrate the concept of orbit monitoring station. So after assess the orbit quality of the observation data, we performed the integrated POD with on-orbit observation. So we use the two types of observation. One is the rail onboard observation of the GPS L1 and L2 and QGIS L1C and L5 observation. And we also apply the IGS network data of maximum 70 stations aligned to the IGC20 reference frame. And I think this is a highlight of my presentation. So this slide shows the carrier phase measurement received from the on-orbit. And the left figure shows the carrier phase residuals using the affixed to the JAXA MJX final solutions. So as you can see, the systematic error are found in the residuals when fixed to our MJX solutions. In particular, we can also see the large systematic error in yellow dot means J07 satellite is located in the GO, and in contrast, the no significant systematic error are observed after applying the integrated POD. And we can also see the orbit differences between the integrated POD solution and our MJX solutions. So we found the significant impact on the along track and cross track of QGIS GEO satellite J07. And according to the plot, along track position of the satellite changed by more than 1 meter. So we So this result indicates the improved observation geometry allows us to identify the systematic error in residuals, and that residuals can correct the orbit error correctly. So I will see another result to using the integrated POD. These two plots shows the SL residuals for the QGSS GEO satellite. So as you can see, the offset of the residuals of the QGS GEO satellite improved from about 14 centimeter to 7.5 centimeter when the space-based observation is applied. And this change is attributed to the change in the along track position of the satellite, I think. So now we are planning to another demonstration mission. At that mission, we will demonstrate the concept of the on-orbit monitoring station to prepare for the ground segment software to hand over to the QGSS ground segment operated by the Cabinet Office Japan. And we also planning to distribute such kind of space-based observation data to the science community, such as IGS, if we receive the permission from the data provider, private company. So I hope we achieve such kind of demonstration and provide such kind of data to the IGS. And this is a summary and conclusion of my presentation. That's all I have. Thank you very much.